Hey everybody, we are going to do homework number 4, practice problem number 1 in this video. So, let's get it started. We are asked to look at the TRB 26 glazed flat plate solar thermal collector, which is made by Sun Earth Incorporated. You say, why are there so many details about this? And that is important because you need to look up this solar collector on the SRCC website. If you Google SRCC thermal, then you will pull up the SRCC website, and in there is the ratings document. There's a document you can download that tells you the rating of this. The SRCC is an organization who's taken this glazed flat plate collector and tested it. And when you download their product data sheet, then you're able to get 2 points you need for an efficiency equation. So the efficiency of our glazed flat plate solar collector is equal to the y-intercept plus the slope times Tn minus T ambient over HP, the panel flux. Whoops. Okay, so, sorry about that. So this is the equation we're looking for, right? But it's not just going to tell us this equation, it will just list the y-intercept and the slope. So when you look on that document, you can find the y-intercept in both SI units and in English units. We are going to work in SI. So when you find the ratings document, you find that the y-intercept is 0.74 and that the slope is negative 4.115. Okay, so we're going to put those into our equation and get the efficiency is 0.740 minus 4.115 times Tn minus T ambient over HP. Now, we're not actually going to use this equation. Isn't that funny? Because what are we asked to do in this problem? We're asked to find, so what are we doing? We're asked to find F, or the fraction of heat provided by solar divided by the total amount of water heating load. And so we're asked to find this F value. And we know L being the load, that's 500 kilowatt hours. We also know the average ambient temperature in the month of January, that's very different, is minus 4.2 degrees Celsius. And we know that the average solar irradiation per day, the average solar irradiation for the month is 104.2 watts per meter squared. So that means for every daylight hour, for every moment of the day, we've got 104.2 watts per meter squared. That's average. Okay, so what we're going to do now is we're going to use the method we learned in class to find F. So the F method. All right, the first thing we do is calculate X. All right, X is equal to the area of the collector times FR prime times UL. These are both characteristics of our collector, right? This is the universal heat loss coefficient from our collector, and this is our factor that accounts for conduction through the collector. And it was remember, initially this was T of the collector minus T ambient, but we said it was much easier to turn this into Tn. But to turn it into Tn, we had to account for the efficiency of conduction through our collector, and that's what this F term does for us. It's kind of a collector efficiency in a way. All right, so we have those terms times delta T, which is the number of hours in the month, times 100 minus the average ambient temperature, all divided by 1,000 times L. I am still sick. Isn't that great? Okay, something I forgot to write is from our document where we got these values, so the ratings document for this specific glazed flat plate solar collector, we can get AC, which is 2.310 meters squared. That is the gross area. We're using gross area because that is what these efficiency terms were determined using. All right, so we know AC, we got that from the document. Now, we need FR and UL, but where are we going to get FR and UL? We don't have that anywhere on the document. Well, that is why we wrote this efficiency equation, because the efficiency equation, this equation, which remember is the Hodel-Bliss equation, is actually FR times alpha times tau minus FR times UL times Tn minus T ambient over HP. All right, so something interesting we're going to look at here is this term is the same as the y-intercept, right? These are just the same constant. This y-intercept would be equal to FR times alpha times tau. All right. Then the slope is going to be equal to that right there. So the slope is going to be equal to, we'll just include that positive in there, is equal to minus FR UL. Okay, so I bring this up because we need FR UL. And so let's connect the dots here. FR UL is the slope minus the slope. So we're just going to take the positive of this, and that is FR UL. Okay. Now, you notice this little prime right here, FR prime. So FR prime just equals 0.97 times FR, and that was just an adjustment that the original authors of this equation had to make in order to make the data fit better. Okay, so what this means is we're going to have X equals the area of our collector, which I believe was 2.310, yes, 2.310 meters squared, times FRUL, which is, right, remember, this whole minus FRUL term was equal to our slope, which is minus 4.15. So FRUL equals 4.15. Those negatives cancel. So we just put 4.115. And from the document, we get this as units of watts per meter squared degrees C. Watts per meter squared C. But remember, this is FRUL. We need FR prime UL, so we're going to add this 0.97 to get that FR to an FR prime. All right, now we need delta T. Delta T, hold this right here, is equal to the number of hours in January. So that'd be 31 days times 24 hours per day. Right? And that is 744. Okay, and then we need 100 minus T ambient, being the average ambient temperature in the month, which we have from the problem statement as minus 4.2 degrees Celsius. That must be in Celsius because this 100 has units of Celsius. Oh, I forgot the units, so that's degrees Celsius. And this right here has units of, see, we did this multiplication, days cancel out, has units of hours. This is unitless, just a number. Divided by 1,000, and this 1,000 has inherent to it watts per kilowatt. That's what that 1,000 is. It's going to convert this number, which is in watts, into kilowatts. And we have to do that because L, our load, right here, is 500 kilowatt hours per month. Forgot to make my document bigger. We'll have to do that in a second. Anyway, so you see how all of these units work out. Meters squared. Let's do this in a different color. We'll do it in yellow. Meter squared cancels with meter squared. Celsius cancels with Celsius. Hours is going to stay because this right here, watts cancels with watts, and kilowatts comes to the top, leaving kilowatts times hours. That's kilowatt hours. Now, we have this per month left, but that's because I forgot to include a unit. This is days per month, 31 days per month. So this is actually hours per month, right? Those are the units there. Those are the number of hours in the month. So these months cancel out, leaving kilowatts times hours, or kilowatt hours, divided by kilowatt hours, which then has units of nothing, which is what we're looking for. X is a dimensionless number, has no dimensions. So those units work out. Always check your units here. And when we plug it all in, we get X is 1.429. All right, we've got X. Deal with me real quick while I make this bigger. Oh, bigger than that. Let's make it double the size. Oh dear. Oh, darn it. I did this wrong. We'll go back to... Oops. Forgive me for doing this while I'm trying to do this. What was it, 112? I don't remember. Oh gosh. All right. Well, you know what we're going to do? We're just going to erase things that we don't need right now. Sorry about this. I should have been more prepared. I was just so excited. Okay, so we have X, 1.429. So now we're going to do step 2, which was calculate Y. All right, so Y is AC times FR prime tau alpha with a bar over it times HP with a bar over it times ND, all divided by L. There's so many terms here that have very subtle meanings. So AC, as I talk about these, I'll circle them in teal. AC, again, is the collector area, the same as this, and we already know that, 2.310 meters squared. All right, let's talk about FR prime tau alpha. All right, so now I wish I didn't have to erase what I had already written, but remember in our Hodel-Bliss equation, we had the y-intercept, and it was added to the slope, times Tn minus T ambient divided by HP, and we got the slope from our document as, we got the y-intercept from our document as 0.74, and it does not have units. Now, in the Hodel-Bliss equation, the original equation is FR alpha tau, right, subtracted from FRUL times this same term right here. So again, the slope is FRUL with that negative. The y-intercept is FR alpha tau. So y-intercept FR alpha tau, which is FR prime alpha tau bar. They're very similar. There's a few things we need to do, but we're close. So you see with y-intercept, we have this term of our equation. But we have to make a few changes. So FR prime specifically is, again, 0.97 of FR. And alpha tau is 0.96 of the real alpha tau. So alpha tau with a bar over it is 0.96 of alpha tau. So you see that FR prime tau alpha bar equals 0.97 times 0.96 times FR tau alpha. So we just plug this in up there where the teal box is, and we're good. Now we need HP bar. HP bar. All right, so HP bar is, in words, the total amount of energy that hits our surface, that hits 1 meter squared of our surface every day. Okay? So that's the total amount of energy that hits 1 meter squared of our surface every day. So to find that, we know HP. What is HP? HP is a flux. It's watts per meter squared. That is the average heat flux on our surface over the course of an entire day. Okay? So that is not an instantaneous value, but an average over an entire day. So we're going to multiply that by the length in hours of an entire day. So remember, this is a heat rate per unit area. So to get an amount of energy, because this is the amount of energy, we need to multiply that rate by a time. And since we're working in units of kilowatt hours, we're going to multiply it by hours. Okay, and like I said, we're working in kilowatt hours, so we need to change this watts into kilowatts. So 1 kilowatt to 1,000 watts. So you see, when you multiply these things together, you get, let's cancel our units. So watts cancels with watts, leaving kilowatts. Multiplied by hours is kilowatt hours. And then per meter squared per day. The amount of energy that hits a surface per meter squared of that surface for an entire day. All right. So we had a value for HP. That was 104.2 watts per meter squared times 24 divided by 1,000 gives us 2.5 kilowatt hours per meter squared per day. This value right here, you can actually get from PV watts. If you put in the size of your surface and the tilt angle, it will spit out this value for you on a monthly basis. So that's what you need for the homework. All right, we're going to erase some of this X calculation. We'll just leave the final answer at the bottom. There's the final answer right there. So we're going to keep that. And we're going to finish getting Y. So Y, again, where did I put it? Oh, right here, is equal to AC, which is 2.310 meters squared, times FR prime tau alpha bar, which we said right here was equal to 0.97 times 0.96. Those are unitless, they're just numbers, times FR tau alpha, which we already talked about, is the same as the y-intercept from the document describing the efficiency of this specific solar collector. And that y-intercept was given as 0.740, and you see it is dimensionless as well. FR has no dimensions. Alpha and tau are both dimensionless. All right, so then multiplied by HP bar, which we found down here as 2.5. 2.5 kilowatt hours per meter squared per day. Then multiplied by ND, which is the number of days in the month. So here's the total amount of energy hitting a surface per day. We're going to multiply that by the number of days in the month of January, which is 31 days, divided by our load, or 500 kilowatt hours. And this would be units of days per month, and this is kilowatt hours per month. Okay, so our units all cancel out, right? Let's do that. Meter squared cancels with meter squared, kilowatt hours with kilowatt hours. Day is in the denominator, day here is in the numerator, month is both in the denominator. It is unitless. Great. So when we multiply all of that together, we get, where's my final number? Oh, it's on the next page. 0.247. All right, we are so close. Now that we have x and y, we calculate f, which the researchers back in the day just ran a bunch of simulations, found x and y for a ton of different possible houses, and then combined all of that data into one really giant collection of data. Then they trained, using machine learning techniques, this equation to get the exact right coefficients so that when you plug in x and y, which we know as 1.429 and 0.247, you get f, which is 15%. All right, that's our final answer. Thank you again for watching. If you have any questions, let me know. This one has a lot of nuances in how we use these numbers.